All right. So now we want to look at how the T-statistic can be used in hypothesis testing and is used in hypothesis testing. But yeah, try to, from now on, keep these two things separate. So, or it's my advice at least. So one thing is the T-statistic as a single value representation of the ratio between the effect and the variance in the data. And the other thing is the T-statistic being used for hypothesis testing and making these binary claims about something, whether something is significant or not significant. Because I think the first use of the T-statistic is helpful. I mean, it's a quantitative measure of effect size versus variability, and you get that in a single number without needing error bars or something. And sometimes you have complex visualizations where it's not necessarily easy to draw error bars. And that T-statistics, of course, are fairly helpful. I mean, even if you think about brain images, if you look at blobs in the brain, and if you think for each where you have a blob, you would also need an error bar, then it's not that easy. I mean, you could visualize the effect and the error on two different brains, but then you have to visually align them in your head and so on. So there, T-static is really helpful. The other thing is then making this binary claim about something being significant or not significant. And there, of course, the question is always how helpful that is. But it's being done, and hence we have to deal with it. So that's now basically talking about the T-distribution and T-statistics for hypothesis testing. Or let's call it for null hypothesis testing. That's this null hypothesis testing. So the first thing, so the way I will do it is first I will talk about the T-distribution and then link our definition of the T-statistic with the T-distribution. That's T versus T maybe. I think it works better this way. So what is the T-distribution? So I have somehow this idea of calling the T-distribution with a lowercase t to clarify that this is different from the uppercase T, which you can evaluate, whether it's in a given data context, whether it's that helpful, I don't know. But yeah, so don't think too much about the big T and the small t, but try to get the concepts. Now, what is the T-distribution? The T-distribution is the distribution of a scalar random variable. So if you have a random variable t, which now has a big T, which is given by this, namely the ratio of another random variable z and the square root of another random variable chi divided by n and the square root of that, then this t has a T-distribution. So what is z? Z is a random variable and is distributed according to a standard normal distribution. And xi, that's xi, sorry, don't get confused. That's a xi, so that's the this thing. That is distributed according to a chi square distribution with n degrees of freedom. Yeah, so we talked about normal distributions, and the standard normal distribution is just the normal distribution with expectation 0 and variance parameter 1. and the chi-square distribution we also discussed, and this random variable C here is distributed according to a chi-square distribution with degrees of freedom parameter n. Now this random variable here, t, that is defined as this ratio, has what is called a t-distribution, and like for the univariate Gaussian and for the chi-square distribution, you can, or one can compute the probability density function, or at least specify it, and it's in terms of the importance of this density functions is a little bit like with the chi-square density function. It's good to know that it's there, but yeah, one doesn't necessarily need to memorize it. So let's use the big T now for the random variable, and then the density function of this random variable is given. Again, it uses the gamma function, and uses this normalization thing here, NP, oops, don't need that, NP gamma n half 1 divided by 1 plus t squared. So this is where the functional dependency on t comes in, to the power of n plus 1 divided by 2. Looks a little bit funky, but if you knew how funky the distributions that are actually used for statistical inference in fMRI using SPM look, then you would think, okay, this is medium funky. The way it looks, and that's fairly familiar, I guess, for you, is that it's centered at 0. It's always centered at 0. So there's something called the non-central t-distribution. That's centered on something else. But the t-distribution that you know from undergraduate statistics, that's always centered on 0. And then you know that for larger degrees of freedom, it approximates the standard normal distribution. And well, that's not too bad. For lower degrees of freedom, it has bigger tails, and I think this is also what you know. So for lower degrees of freedom, it looks a little bit like this. And the important thing is here that in the tail, it's larger than in the case for high degrees of freedom. So this is n small. So I'm not doing it now really parametrically, but more intuitively for this. And this is n large. And you might remember that from approximately 30 on or so, the standard, so n being 30, the standard normal distribution and the t-distribution are virtually identical. So yeah, which then essentially, if you're larger than if you have a sample size larger than 30, it doesn't really make sense to do t-tests anymore. Then you could also do simple z-tests. So the t-distribution, I think I write it in general like this: t over the random variable, and then as a function of the degrees of freedom. That's the t-distribution. Of course, what you have here, this is somewhat reminiscent, and of course this is also how it was designed, to the T-statistic that we discussed earlier, but it's not that simple. Yeah? So keep these two things separate in your head for the moment. At one point we defined the T-statistic, and we have some we have some meaning with it. Now we learned about something different, namely the t-distribution, which has a probability density function and is defined as the ratio between a standard normal distributed random variable and a chi-square random variable. Now, how do these two things link? This is, of course, the question. And this is what we're going to do now. Questions about this t-distribution thing? No. Good. Then let's call it the T-statistic null distribution. So now what we are thinking about is how the T-statistic that we just have defined, namely we defined it, now a little bit brief, we defined it as this. We want to think about how this is distributed under certain circumstances or under specific circumstances, maybe a given value of the beta parameters. So what we are doing here is the same thing as we did for the beta parameter estimate. We thought about how is this distributed, how is this distributed, and we found that it's distributed as this, right? And we had some intuition what that means. So it's centered on the true but unknown beta parameters, and it has a variance that scales with the true but unknown variance, and it has a normal distribution. Yeah, so we've seen something like that, and now we are thinking about how the T-statistic is distributed. Yeah? So we are basically doing the same thing that we did previously, now for a different entity. A slight difference, though, is that we think about the distribution of the T-statistic under a specific condition, namely that the true but unknown value for the beta parameter takes on a specific value, yeah, and this we call our null hypothesis, and basically we can write as simply this. So we are thinking about how the T-statistic is distributed if the true but unknown value of beta equals beta 0. Yeah, maybe I just write that in words here, then it gets clearer. 0. Assume true but unknown value of beta is beta 0. Yeah, and we ask what is the distribution of T. And the first thing that we have to do, the first thing that plays a role now, if we want to use the T-distribution, so if we want to use this thing, we want to use the T-distribution, is that we have to modify our T-statistic somewhat. Because if we are now interested in assuming that the true but unknown value of beta is beta 0, and beta 0 is some value, I don't know, something like 10, for a univariate case, then of course, if we estimate it by beta hat, we will get something like 10.5, 9.7, and so on. But this will never be centered at 0. So we have to we have to center our T-statistic at 0 to actually get the T-statistic into the format that is appropriate for T distribution, where of course here the 0 plays a role. So we now have to modify the T-statistic by including the true but unknown null hypothesis assumption in its definition. So we need to subtract the null hypothesis assumption about the true but unknown value in the numerator. So this might be a little bit confusing, but it will hopefully get clearer in a second. Because usually the null hypothesis is that beta 0 is 0. Yeah, that's what people call a nil hypothesis also, right? So if you looking for a difference between two parameters, so for example you have beta 1 and beta 2, and you are looking, you want to evaluate the difference, then as discussed previously, you could use a contrast vector 1 minus 1, and then you would get beta 1 minus beta 2. If you are interested, maybe that was not a good example, I don't know. If you are interested in the case, that wasn't really a good example, because in this case the beta 0 and so the beta 0 would not be 0, but they would be identical, so they would be of this form. So here you get 1 minus 1, and then you get A minus A, so you get 0. This is the logic of fMRI testing, but that maybe wasn't that helpful at this point. Here, if you think about again the one sample thing, thing that we saw with the univariate Gaussian, then of course you can interpret what we have here as CT beta hat minus 0. So you can view this as the case where you make the null assumption or the null hypothesis that the true but unknown value is 0. But you want it more versatile, and you want to be able, if you express it in undergraduate statistic terms, to test against other values than 0. So maybe test against a value of 3 or 4 or something. So this is why this extra CT beta 0 comes in. Yeah, so it shifts the distribution. So you cannot view it differently. So you, if the true but unknown value of beta is in fact beta 0, then the distribution of beta hat is shifted to 0. So maybe that's always a hassle to explain this, but in principle it's fairly simple. So assume that beta 0 is 5, then roughly our beta hat is distributed around 5, because it's trying to estimate that. Now by subtracting beta 0, our beta hat is now distributed around 0. Yeah, and we need to do that because the T distribution is only specified is centered on 0. Yeah, good. So I tried many ways to explain this. If it confuses you, then ask, and I try to explain it in a different way. So this basically now allows to assume anything that we want as for the null hypothesis. Now what we have to think about is to essentially get our T-statistic into the form of the T-distribution, namely that we have something that is univariate normal distributed with a standard univariate Gaussian and divided by something that's chi-square distributed. Now, this thing, so maybe let's look at the numerator first. CT beta hat minus CT beta 0. It's fairly intuitive to see that this is has an expectation of 0 now, because under the null hypothesis, you always have to, this is in the problem of classical statistics, you now always have to build in if beta 0 is in fact the true but unknown value. If beta 0 is in fact the true but unknown value, then beta hat is of course centered on beta 0, because that's what this says. So it's around 0. It's also univariate, which is good, but what about its variance? Now, the variance, we know what the variance is, right? So we know that the variance is this, and this is of course not 1, which is required for the T-distribution. So what can we do to get the distribution to have a variance of 1? Yeah, does any one of you remember what you can do if you have some random variable and you want it to make it distributed according to a univariate Gaussian, a standard univariate Gaussian with expectation 0 and 1? Do you remember? There's a term that you, there's a procedure that you learned in undergrad statistics. Does anyone remember that? Exactly, yeah. It's a Z transformation. So what Z transformation does is, if you have something like this, and you want to get a new random variable that is distributed according to this, then what you have to do is, do you remember also what you have to do to the values?
It would make sense to divide by the variance, but I'm not sure.
Yeah. So you divide actually by the standard deviation, and you, because this square transformation comes in always when you multiply something, and you need to shift everything, and this is what we did here, by its expectation. Yeah. So if you define Z to be x minus this value and divide by the standard deviation, then Z is distributed according to a standard normal distribution. Yeah. And this is what actually has to be done. And this division, this subtraction of beta 0, that does this shift in terms of the expectation. And now we have to divide by the standard deviation. So what's the standard deviation of beta hat? This thing, so this thing here, so that, and another thing that comes in here is that, of course, we need to carry our CT over. So we have to factor our C in, but if we divide CT beta hat minus CT beta 0 by the standard deviation, so the square root of the variance, then we already, or then at least we have our T-statistic, or our we will get to, let's say it like that, we get to something that is standard normally distributed. Yeah, so this thing here is distributed. I'm not writing this up again, but this is distributed according to a normal distribution with expectation 0 and variance 1. So again, why are we doing this? Because we want to somehow bring together our T-statistic with the definition of the T-distribution. And for the definition of the T-distribution, we need something that is standard normal distributed with standard normal distributed, so expectation 0, variance 1. And then what we need to do is to divide this, if we want to create a T-distribution, to divide this by something that is chi-square distributed with n degrees of freedom. So, of course, we have something that is chi-square distributed. Namely, we have our normalized version of the variance estimate that is chi-square distributed. With n minus p degrees of freedom. And if we now divide this thing, and we might call that z, maybe a big Z, by our variance estimate divided by n minus p, we get the following. It's not the nicest presentation because it's not used as a proof, but it's more like we do this, then we do this, and something happens, but you will see what we get in the end, and then it all makes sense. So if we divide this thing by the variance estimate, by the square root of the variance estimate, then we will, sorry, I need to check what I'm doing here. Now I confuse myself. This is chi-square distributed. Delete this, and then why do we? One thing that I'm wondering. Sorry. Now I know why I confused myself. So I wondered why I'm dividing by the square root, but of course the T-distribution is defined in terms of you have something chi-square distributed, and then it's the T-distribution is defined in terms of a random variable where you have something standard normally distributed divided by the square root of something chi-square distributed. So, and divided by its degrees of freedom. So now I'm back on track. So we want to now divide, we want to put in something chi-square distributed, and what is chi-square distributed is actually this thing. So this is chi-square distributed, so we put that in, n minus p divided by sigma square, sigma head square, and we divide that by its degrees of freedom, because this is what the t-distribution requires. So the t-distribution requires something standard normally distributed, something chi-square distributed, divided by its degrees of freedom, and the square root taken. And this is what we are doing here. So let's get rid of this and this. So this, in terms of what we see above, this thing, that's our z, that's our xc, and that's our n. And what you see there is the c divided by n square root. So going back here, so exactly this thing. Now if we do that, what do we get? And this is what we want to look at now. So if we do that, so of course we can write it a little bit different. So we can just put the n minus p up here and have this divided by n minus p sigma square sigma head. And then what we have, so this is both, so this is a square root, so we can basically put it together and take apart and so on. So we have here sigma square, and here we divide by sigma square. Maybe we can first, if you want, we can write it as a long square root. So we have sigma square ct xt x minus 1 c n minus p sigma square sigma head square. And in the numerator we have c minus times n minus p. So what we have here is that this true but unknown value for the variance, that this cancels out, and we get in the denominator, we get ct xt x minus 1 c times our variance estimate and our n minus p, and here we get ct beta head minus ct beta 0 times square root n minus p. And then we can as well take this to the power of minus half apart. And then this cancels out, and we get to what we actually defined as our t-distribution. Our T-statistic. Need to get warm again for teaching. So, what did we do here, and why was it so complicated? We wanted to create something. We wanted to follow what the t-distribution requires. So the t-distribution requires something standard normally distributed, so this z, and something chi-square distributed, divided by its degrees of freedoms and the square root. Now, if we do that, so if we z-normalize our beta hat estimate and put in our distribution for the variance parameter, which is chi-square distributed in the scale version, then we can reformulate the whole thing and find that actually what we call the T-statistic is distributed exactly according to this thing, and this thing is of course called a T-distribution. Yeah. So what we've shown here, and maybe not in the nicest way, but at least we've shown it, is that the T-statistic, as we have defined it here, is in fact distributed according to a T-distribution with, and that's important, with n minus p degrees of freedoms, because our degrees of freedom for this variance parameter was n minus p. Yeah, it's magic. So we can write this here as maybe whatever n minus p, p, which refers to this n minus p. So I did it basically. So this is actually this is not easy, because this is what student published in the beginning, that if you have this, how does the probability density function for doing something like that look? So if you have beta parameter estimates, you have a variance parameter estimates, how does the distribution of this T-statistic look? And the most amazing thing about the whole thing is that although both the beta parameter estimate and the chi-square estimate in this normalized version depend on the true but unknown value of the variance, the distribution of the T-statistic does not depend on true but unknown values besides the null hypothesis. Yeah. So this, so these kind of distributions, so the distribution of the beta estimator and the distribution of the variance estimator, you cannot specify without knowing the true but unknown values. Yeah, so you can simulate them and so on, but you don't know them. Given the fact that beta 0 is in fact 0, the T-distribution you can specify without knowing the true but unknown variance parameter. And that's quite an insight. And we did not do it in the way that this was originally done, that you basically think about this probability density function and this probability density function and then transform them, put them together. We said, okay, we know that there is something that is T-distributed. Now, how can we create something that fulfills the criteria for something T-distributed? And it turns out that the definition of the T-statistic as we had it fulfills this criteria, which is of course because that's how it was constructed. So I think more people looking at their phones than at my stuff, which is maybe a time to then go again to some intuition and to finish. So how is this now being used? Of course, it's actually being used, as you know, that you say, okay, I assume my beta 0 has some value. Then I know that this T value here is distributed according to a T distribution with n minus p degrees of freedom. Now a T distribution looks like this somehow, so it looks very much like a normal distribution. And now I compute a T, and let's say I compute a T that is here, so let's call that T star. Then you can say, well, if beta 0 is in fact the true but unknown value, then observing a T star of this size or something more extreme has a relatively low probability. Yeah, so this is then what you would usually call your p-value. And if this probability is less than, let's say, 0.05, you would say, okay, observing this t-star under the null hypothesis that beta 0 is actually the case is not very likely. So maybe the null hypothesis is not true. So that's the basic idea of null hypothesis testing. But of course, that's you will never know what is really going on, because of course this happens under the null hypothesis in 0.05% of the cases. And this idea of null hypothesis testing, of course, one can formalize much more and talk in more detail about it, also with respect to what is actually the number of false positive given a given criterion and so on. So there's much more that one can talk about null hypothesis testing, but the basic logic is always as discussed here. So you have some statistic, you can specify its null distribution, and then you evaluate your statistic under the null distribution. With the t-statistics, you can do that, but you can also view the t-statistic, as we did in the first hour, as purely as a measure of effect versus data variability. So there are these two things, how t-statistics are being used. What the effect really is, that always depends on your beta parameters, and then also, of course, on your contrast rate. So your specific t interpretation depends on the setup of your GLM and your contrast. So there you always need to basically understand the whole thing, and then for your specific GLM, for example in an fMRI analysis, think carefully what these beta parameters refer to and what the contrast vector then does with them to interpret the essentially the color of the blobs that you then see on your statistic parametric map. But essentially that's the story about t-statistics. Questions? I think I've shocked you a little bit with this transformation of the basically showing what this thing was about. So this, with these equations, that was to show that this thing is actually distributed according to a t-distribution, which is well, you can believe people telling you that, but you, based on the definition of the t-distribution, this thing actually shows that this t-value is distributed according to a t-distribution, if the null hypothesis is true. All right, good. So no questions, then let's stop that here. And next time it's F statistics, actually.